Well, welcome to the colloquium, and I'm very pleased to introduce distinguished Professor Elisabeth Sikes from Rutgers University. She's in the Department of Marine and Coastal Sciences. I have to look because like our school, the name of the Rutgers Marine Group has changed over the years, so I have to make sure that I got it correct, and it is a department now officially. It was an institute, if I remember correctly, formally. And she's been at Rutgers. Well, she spent the first 10 years of her career actually in the Southern Hemisphere, which I was interested in learning. And you started out in Tasmania, and then Auckland and New Zealand. So she was close to the place that she's going to talk about today, which is the Southern Ocean. She did her undergraduate work at Wesleyan, which I also didn't know until I read her CV there, and I received her PhD in the joint program, MIT Woods Hole program, and then went on to the Southern Hemisphere thereafter. She's extremely well known for her work in particularly in paleo reconstruction, paleo environment reconstruction, and oceanographic processes, particularly in the Southern Ocean. And she's going to tell you a lot about that today and how it relates to climate dynamics, which I think is a big emphasis of our own program here. So it should fit right into this. And what else? She's won many awards. Would you like me to go through the various awards?
If you wish.
Oh, and she's also the president-elect of the Geochemical Society. And so she's now the vice president, but rotates into the formal presidency in a couple of months, actually. And so she's been very interactive in the community of oceanography and biogeochemistry, geochemistry. So I'm really pleased that you're able to come today. And you know, there's I think I met you in an earthquake.
Well, that's right. That's right. In New Zealand.
In New Zealand, right. And we all thought we just drunk too much the night before. But in fact, we were doing this kind of thing in the room. So I don't think we'll have that today here, but you never know.
You never know. It's Friday the 13th, as the technical issues have already demonstrated.
So welcome.
Thank you.
Yeah.
So Bob's actually given away my secret. I usually say, yeah, I've been working in the Southern Ocean since my PhD because of the science, but part of the reason the science was so compelling is I was living in Australia and New Zealand for the first decade and a half of my scientific career. But the scientific reason that I've been looking at the Southern Ocean for the last 20 years. And I'll stop here because I'm going to go through a lot of different proxies for paleo stuff. I'll do anything to learn more about the Southern Ocean. I started off looking at sea surface temperature, but I'm looking at a lot of other stuff now. But the scientific reason that the Southern Ocean is so important is it's where most of the deep CO2 in the ocean exchanges with the atmosphere. And so what I'm showing here now, let's see if I've got, yes. So what I'm showing here is one of the most, we know that the ocean holds 50 times, the deep ocean holds 50 times more CO2 than the atmosphere. And what I'm showing here is one of the most important paleo climate records of the last 40 to 50 years. This is the CO2 in the atmosphere measured in air bubbles in ice cores. And what the important thing about this is, and is this the pointer? Yeah, okay, yeah. So the important thing about this record is what it shows is that 20,000 years ago in the last glacial maximum, CO2 was a third less than it was pre-industrial. Frightening to remember, but pre-industrial is 280 parts per million, not where we are over 400. So, and across the deglaciation from the LGM, which ended about 18,000 years ago, we can see the CO2 rise really rapidly. It increased by a third in less than 10,000 years, which on geological timescales, that's really fast. And even when these records came out in the early 80s, late 70s, early 80s, it was clear that if the CO2 came up that fast, it had to have come out of the ocean. What's also important for the last 40 years of work is this step change. So what we have is the last glacial maxima ends here, and during Heinrich's day, the one I'll go back to this, but there's a rapid change, a jump here at about 16,000 years ago. There's a pause during what we're calling an Antarctic cold reversal. There'll be a test. And then again, another increase in the last phase of the deglaciation, which is the younger dryas. But before I torture you all with paleo CO2, let's talk about, because this is an oceanography department. So let's talk about why the Southern Ocean is where the ocean exhales. That's what I like to say. It's where the ocean exhales. So the first part of this talk, I'm going to give you a little tour of tracers for CO2 in the ocean that we use and can use in the paleo record, and the evidence for the change circulation. So why is CO2 sequestered in the deep ocean? It relies on the deep conveyor belt. I hope you've all seen this figure. This is the one I use in classes as well, and it teaches us that the North Atlantic deep water forms in the North Atlantic, and it travels down the Atlantic Ocean, and it rises up, comes back to the surface. And along that journey, most of you should know that it picks up CO2. But in order to really understand how it works, we have to stop thinking about the world like Wally Broker. He was the one that made this famous. And we have to look at the world like Lynn Talley. And so I would never show this in an undergraduate class, but let me unpack this for, oh, no, I don't want to go for it. I want to take my pointer. Okay, so North Atlantic deep water. Purple is surface water. It sinks in the North Atlantic. It travels down the ocean, and it rises in the Southern Ocean where it exchanges some CO2 and sinks again as Antarctic bottom water, our blue arrow, and it goes into the two other basins and the Atlantic, but importantly, it goes into the Indian Ocean. The water that enters the Indian and Pacific Oceans is Antarctic bottom water, not NADW, and it comes back at mid depths to then recirculate and resurface with its extra CO2 load and exchange and form our intermediate water masses, which I think should be in my next slide. So what we have here is the circulation in the Southern Ocean. And I know most people don't know this in detail, but the Southern Ocean is a 3-layer ocean, 3 to 4 layer ocean. So this is our NADW coming up in the Southern Ocean. It upwells both through wind-driven upwelling, and it simply outcrops because of density there. And how long it stays at the surface is how much exchange you get down there. And so we have the water coming back, recirculating from the Pacific and Indian Oceans, rising up further north than the NADW, which is sufficiently dense that it forms Antarctic bottom water. Okay, we also have these shallow water masses where they lose density. So it's really a reflective of global balance between this physical ventilation and our biological drawdown, which comes next. But water that loses buoyancy moves north as Antarctic intermediate water, and above that subantarctic mode water. Okay, so those are the recirculation that we've got in the deep ocean, in the Southern Ocean. How does this the CO2 affect us? So the biological pump is working on this water as it's traveling down from the North Atlantic. So the biological pump is the process by which photosynthesis takes up CO2, turns it into organic matter. It sinks, and at the depth it is respired and back to CO2, and that is the CO2 that can fizz out of the Southern Ocean or exchange out of the Southern Ocean. We can introduce now, I can introduce our tracer, C13. It's really very simple. In phytoplankton, significantly discriminate against the heavier stable isotope C13. So during photosynthesis, so that organic matter that sinks has a very depleted signal. I can give you a number. You don't need to know it, but -20. So all of that CO2 that is respired back out retains that organic signature. And so as you travel around the deep ocean and it gets respired CO2, that's how it's trapped, it retains that depleted C13 signal, which we can trace in the DIC of the ocean. So when the upwelled water degasses, its signal is reset and entrained in these shallower water masses, but farther south where we don't have as much exchange, that we retain some of that CO2, and NADW has both a higher CO2 than NADW, and it retains that signal of the C13. So as I said, the atmospheric CO2 then reflects a balance between this biological drawdown and physical ventilation. So if in the past you change either your water mass, oh yes, and it transports that when you have that water, it transports it. So if you change the physics of the Southern Ocean, you are going to change how much CO2 is getting out down there, not so much how much is going in, because it goes in everywhere. It comes out in the Southern Ocean. So if I show you my C13 signature for today, you can see, and I put this on here to help. So the more depleted our signal is, the more CO2 and the less ventilated it is. And the more enriched our signal is, it's got less CO2 and it's more ventilated. So if I put a line on it, you can see that this bolus of, and I've got the Atlantic and the Southern Atlantic and the Southwest Pacific here, and that bolus of enriched low CO2 water coming out of the Atlantic as NADW sits here at about 3,000 meters, and you can see the Pacific is going the other way. And just for completeness, that we also see another low CO2 signal here in the intermediate water that's has exchanged and lost most of its CO2 in that recirculation that is the Southern Ocean, or the washing machine that's the Southern Ocean. So in order to understand why we have this deep NADW in the Southern Ocean, we need to think about the special circumstance of Drake Passage, as Lynn Talley calls it. So the Southern Ocean, the Antarctic Circumpolar Current, which runs around the Southern Ocean, yes, which runs around, is geostrophic flow. So it's in balance with the wind forcing. It reaches to the bottom. And so you can't have a net meridional transport across that Drake Passage without a pressure gradient. And you can't get a pressure gradient if you don't have land somewhere. And so I'm a descriptive oceanographer. I do have some equations if you want them for discussion at the end of the talk. But basically, the only way the water can get across Drake Passage is below the sill. So if I do this in the descriptive fashion, so the modern Drake Passage dynamics is that the ACC runs to the bottom, and North Atlantic deep water can go underneath that sill. So it can only get into the Southern Ocean below the depth of Drake Passage sill, which is about 2,500 meters. And then it can turn and form and circulate around the Southern Ocean, as anyone who works in the Southern Ocean knows. So that means that fundamentally it's the densest water there, besides the stuff that gets denser on the shelves in the Antarctic bottom water formation zones. Anything shallower than the sill gets swept into the ACC and can't cross the core of the ACC. It can only get across the ACC by eddy processes. And so, it just doesn't. Okay. So today we have North Atlantic deep water coming in. It fundamentally fills the Southern Ocean as lower circumpolar deep water. That's what we call it once it's down there. And then it is the dense salty water that gets chilled and then forms Antarctic bottom water. And so we can look at the mechanics of this in my C13 space by comparing two. Oh yeah, I'll come back to that. So I'll come back to it. So fundamentally, if we do look at the Sputnik diagram, what we see is NAD. Whoops, I pushed the button. Not the. Okay, I have to go back one more. Sorry, got ahead of myself. Okay, whoa. All right, so push the arrow, not the forward button. So if we look at the ocean as a whole, the Southern Ocean connects all of the oceans. And if we start in the Atlantic, and by the way, this is salinity here, not CO2. So we have NADW, it rises in the Southern Ocean. If it loses buoyancy, it's Antarctic intermediate water and mode water. And if it gains buoyancy, it becomes Antarctic bottom water, which fills all of the basins and returns as upper circumpolar deep water in the return flows. So that's today. Okay. Now, having told you about C13, this is another paper this is a paper that's been cited 1,000 times. And basically it's a classic because Bill Curry and Delia Apo use C13, and these are the core. This is your database here, and they were able to show through the C13 low C13, which is our warmer colors here near the surface, is water with less respired CO2. And they were able to show in this wonderful paper that that bolus of deep water that we know is coming out as NADW today was shallower in the LGM. And if in my world of helium, it's shallower than the sill depth of Drake Passage. And in fact, what the conclusion was 20 some years ago was that, you know, we had this shallowing of North Atlantic deep water, and so the deep basin filled with Antarctic bottom water. That interpretation hasn't changed, but this is the Atlantic, not the other basins. So if you move that forward to our understanding of Drake Passage, if we have NADW that's shallower than the sill, then it can't get into the deep ocean. And so what would have happened to that North Atlantic, that glacial intermediate water, North Atlantic intermediate water, GNAAW, it would have had to have turned and entered the shallow circulation north of the ACC. And so whatever formed Antarctic bottom water back then cannot have been directly derived from North Atlantic deep water. Okay, that's pretty radical. That reminds me to say, not to forget to make the main point. So if we take away that circulation of the that deep circulation and not allow it to enter into the Southern Ocean, then we have to ask what formed those deep waters. And so we can look at those by looking. What we did in 2016 and 17 is we produced a depth transected course here, and then we compared it to a depth transected course here and looked at the difference in the structure of the Southern Atlantic and the Southwest Pacific, and looked at it through time. And so this is to remind you to say, to put these things, we need to have some paleoclimatic vocabulary. So I've introduced to you the circulation of the Southern Ocean and the premise that the circulation had to be different in the last glacial maximum because North Atlantic deep water was 1,500 meters shallower and could not have fundamentally entered the ocean. So to introduce some pieces of paleoclimatic vocabulary, I'm going to show you this figure from Chacun et al. 2012. Now this is a little bit of an older paper, and so what we have here is their atmospheric CO2, and it's a little bit of a rougher. We're 10 years ago, right? So it's a little bit of a more sparse record, but you can still see in this record, in the CO2 record, that we had a last glacial maximum plateau. It started to rise, and then it paused, and then it rose again. And what they were doing in this paper is what I can use to unpack our paleoclimate vocabulary. So we have LGM, last glacial maximum, and they're ice core people, so they run time the other direction. So just note to self and to you, sometimes the time scale is going to go back and forth. Sediment cores, we tend to run it the other way. Okay, so we have the last glacial maximum here on the left. And then at the time that the CO2 started to rise up, it was a time of coldness. Okay, so he was unpacking the temperature record of the Northern Hemisphere from the Southern Hemisphere. And so at this time of at the very tail end or at the beginning of the deglaciation, the Northern Hemisphere cooled. And that's called, in this world, he was calling it the Older Dryas, but we now call it Heinrich 1. Okay, and at Heinrich 1, interestingly enough, is time of shutdown of North Atlantic deep water even more. That intermediate water paused even more. And we see great warming in the Southern Hemisphere while the Northern Hemisphere is cooling. This is this bipolar seesaw that we observe in the deglaciation. And so then the next time is what I call the Antarctic cold reversal, or we call, those of us who work in the Southern Hemisphere, it's a pause. It's not shown so well here because this is terrestrial records, but we see this pause in the warming in the Southern Hemisphere, and we see the bowling alley rod, BA, in the Northern Hemisphere. And so we have Heinrich 1, Antarctic cold reversal, and the Younger Dryas, which we really don't see much of a reflection of in the Southern Hemisphere. But the timing is really important. This is starts from 18 to about 15,000 years ago. This runs from about 14.2 to about 12, and then we have the Holocene starting at about 11,000 years. There will be a test. Okay, so back to my story. The Southern Ocean is where the ocean exhales. And the next part of this is evidence for that enhanced glacial CO2 sequestration so I'm actually going to show you some of my data. And then we're going to look at evidence for the release of that CO2 when and where versus, and so the timing of that release gives us a clue as to who was driving the bus. And because I've presaged it, I'll presage it again here, the locale of that ventilation, we didn't all come out in a ring around the Southern Ocean. It came out in different places, it looks like, at different times. Okay, so this is, again, so this is one of the most important Southern Ocean records. This figure has been reproduced, I think, 1,100 times in papers, because it's just so defined what we're looking at. So now that I've given you the tools, you can see that this color, this box here, is basically the whole deglaciation. And what this is showing us, it's from the South Atlantic sector of the Southern Ocean. And I'll show you its location in a little bit. But the main thing is we don't see, this is opal flux. So opal flux comes from diatoms. Diatoms are phytoplankton. When we see lots of opals, the diatoms are going crazy and reproducing like crazy. So they're using this productivity signal as a signal for upwelling, because for those diatoms to get this quick charge and reproduce very rapidly, they need nutrients, and that upwelling in the Southern Ocean brings nutrients. The Southern Ocean is probably the largest high chlorophyll, high nutrient, low chlorophyll H&LC zone in the ocean. So anyway, in the LGM, not a lot of productivity. And then here we come into the deglaciation. Wow, it goes right through the roof. And I can tell you right now, I'd like to put my line on there now before I forget. That line where it really kicks in is a little bit into Heinrich 1. It's 16.5 thousand years ago, 16.5, remember that number. And so that's our Heinrich, where it was warm. And then this is the Antarctic pole reversal, where everything sort of shuts back down, not completely, but it shuts back down. And then after the Antarctic pole reversal, it kicks back in and continues on through the rest of deglaciation. So this is a record of productivity. That productivity would have indicated upwelling. And if you're upwelling water, even if they're productive, you're still releasing what was in the deep ocean. So what's the evidence for CO2 in the deep ocean? I'm going to show you. So this is our depth transect. To give you an idea of how we did it. I showed you where this transect was on the map. This is off of New Zealand. The oceanography on here, so the salinity and the C13 is from the WOS section, and that's the bathymetry in black. And then if we go just a few degrees to the east, we run into New Zealand, and then we have sediments that we can core. So we cored down the slope of the North Island, and we added one off to the east and the west. But basically we have a depth transect of cores with which we can recreate the oceanography in the past. And it gives us, and what you can see here, the last piece is these colors are the C13. And so you can see here that that's the salinity of the lines, but you can see that signal of enriched C13 at the surface and pressing down into the ocean as AAIW, and then this very depleted C13, that's my Pacific deep water returning at depth. And so my deeper cores are going to show you that signal, that C13 signal. Okay. And so this is our, yes, and changes in, I want to remember to say, changes in ocean circulation or winds can affect the CO2 signal. And so the C13 signal in these subthermocline waters, right? I've already talked about the exchange at the surface and how we reset that signal. So this is our depth transect. I'll just walk you through this one slowly, and then the next one a little bit more quickly. But these are each of our cores. That's the data points. And that's, so we've got a core at, 500, 1100, and so on. So each of those are our data. And then we go back through time. And so these warmer colors here at the top. So if we look here at today on the left, we see that really ventilated, enriched C13 signal of the mode water and the Antarctic intermediate water down to about 1,500 meters here in the Pacific. It sits down about that deep. And we see more depleted water below, like I showed you in that vertical transect. So if we dial back to the LGM, you can see this highly increased or a highly depleted, much more depleted signal, which shows us that's our CO2 in the water. What we can also see is that the depth of that water. So today we have AAIW ventilated. In the LGM, it's only mode water. So this water didn't get ventilated. And then to follow on from that, but we see this pulse of ventilation here at 16.5 thousand years ago. And then if you follow this through, what you can see is it snaps that shallow ventilation snapshot at, and this is our Antarctic cold reversal. So this is our Heinrich, where we see that first jump of CO2 out of the ocean. This is the ACR, where we see a pause. And then what we see here is we're cleaning out the rest of the ocean. So right after the this pulse, we start to see that more enriched CO2 entering the ocean. So that's the signal of ventilation in the deep ocean in the Pacific. Now, if we go to that set of cores from the Brazil margin, it's a completely different ball of wax. So first of all, let's start with the today so that we can see it. What we can see is what I showed you in those two profiles, a very enriched Antarctic intermediate water signal here at about 1,000 meters. And then that's that big bulge of CO2 low, CO2 and enriched CO2 today. And in the LGM, this is the signal, a time transit signal of what I showed you from Curry and Oppo. And what you can see here is in the LGM, we've got our shallow, somewhat less depleted. So somewhat, it has low CO2. It's coming, that's our glacial North Atlantic intermediate water, and that's our shallow signal. And so if I draw an arrow on here, what you can see is North Atlantic deep water was a lot shallower. It was North Atlantic intermediate water. And then through that period where we're seeing all this ventilation in the Pacific, we're seeing pretty much nothing going on in the Atlantic. It kind of like pauses. That's our Heinrich, where we had a shutdown of the water. And then we see it drop after the bowling alley or after the Antarctic cold reversal. We see that deepening and strengthening of Antarctic North Atlantic deep water that's going into the Holocene. Okay, right there. And that's after the younger drives. So AMOC reinitiation or Atlantic meridional overturning circulation was late to this ocean degassing. And this is a figure from a review paper we just published, but I just want to put this all together for you. So there's our CO2 jump at the same time that we see that upwelling jump in the Southern Ocean. I'm going to come back to the sea surface temperature later, but here you have this signal of AMOC strength, and you can see it really just, the going down is it's slower. This is just protactinium thorium. It's a transport tracer that other people use. I do not, I just believe in it. But we can see that during the glaciation, we had some transport. It really stopped in the Heinrich, kicked back in after the ACR. So that's the timing. So really, I want to emphasize that what we're seeing in the Atlantic is the Atlantic's transport signal, but we're not seeing it in the other oceans. So yeah, so that's to remind me to talk about the upwelling. So we're seeing this signal of upwelling and CO2 escape when the North Atlantic is basically not putting out any water to the Southern Ocean. So if you accept my hypothesis that the Atlantic wasn't driving the bus like it was today back then, what was the role of the Southern Ocean? Let's go back to this figure so we can see. So today, this is the one I showed you. We have our bolus of NADW enriched water here at 3,000 meters. I'm going to show you dueling transects. So now I'm going to put the North Atlantic, that Atlantic time series I showed you, and the Pacific time series in time slices. So this is just C13 evolution. The dotted line is the Atlantic, the solid line is the Pacific. I'm going to just run through that data again in a different way. And so the first thing to take home from this is in the LGM, there's our intermediate water, our transport out of the Atlantic Ocean. And let's look at the Heinrich. Okay, oh no, yes. And so the other thing is the Pacific was much more depleted than the Atlantic today. Okay, at the bottom, even then, even in the LGM. So there was some extra signal. And so if I just roll you into the Heinrich one, where I told you that there's no transport out of the Atlantic, what you can see is, yep, that transport's gone. That signal disappeared. But the Pacific is ventilating, right? If I move this way, if I move towards the right on my slide, I'm ventilating. And the Pacific is ventilating at the bottom. In fact, it's almost the same as the Atlantic in the Heinrich. And there's our shallow pulse I showed you from my Atlantic. There, it's actually more enriched than the Atlantic. So it's like I like to say, It didn't care what the Atlantic was doing. It was driving its own bus. So here's our Antarctic cold reversal. Similar thing. The Pacific is moving towards ventilation, and the Atlantic's kind of going, you know, holding still and flapping around. Here's the Antarctic cold reversal to the younger dryas, and that's when we finally see the Atlantic move. And then this is our modern signal. So yes, so through the early part of the deglaciation, the Pacific was driving the bus, and the Pacific deep water comes from the Southern Ocean, not the Atlantic. So let's look at that. So if AMOC wasn't driving the release, what is the evidence therefore for that we can? I'm going to now supplement my C13 data with evidence for early oxygenation and CO2 release from the Southern Ocean and mid-latitude warming. Why was the Southern Ocean, the two other sectors of the Southern Ocean leading? Because we had early mid-latitude warming, and I'm going to show you evidence for that. Okay, so back to the South Atlantic, however, because that's where most of the Southern Ocean people work. And this is the Jacquard et al., another paper. But this is that same record, right? And it's the same core, actually. So we can use as evidence for bottom water oxygenation. We can use as a signal for release. Because, right, CO2 and oxygen are inversely related in the deep ocean, right? If you need oxygen to respire organic matter. So when we see a reoxygenation, we can assume that we're losing that CO2. That CO2 is not there. It's escaped. And so this core, long story short, the main thing I want to show you on this is this manganese record here. And so manganese is soluble in disoxic water. So if we don't see it in the core, that means what we see, it resedimented in a core that is oxic. It means it had a disoxic phase that became oxic and then it resedimented. So it had to be resolubilized and then reprecipitated. So these signals are showing you here, when you see this signal, that's when we saw the oxygen reintroduced into the sediments. Now, there's a lot of other stuff to unpack here. And again, I am not the manganese chemist. There are other people in the room who are much better at this than me. But the point being is, yes, it has to do with sedimentation rate. It has to do with a lot of other things. But let's for now assume that this signal is sin-ish depositional. It's happening at the same time. And so there's the signal of upwelling where we see the CO and the CO2 release, that rapid pulse of CO2 release. And what we see in the deep Atlantic is that that oxygenation didn't happen until the younger dryas. So that was the work from 2016, and you can see it's 7,000 years later. And so that cannot be sedimentological. Okay, that we've done some of the calculation. So the Atlantic oxygenation is late to the party for our upwelling and CO2 release. But the work that my postdoc Aidan has been doing, Aidan here, he went to other sectors and he found a signal from the Southwest Pacific, so just south and a little bit east of New Zealand in the Southern Ocean. And that signal of manganese redeposition, or that oxygenation signal, is happening arguably about 20,000 years ago. And then these are our cores from the Indian Ocean. It's a little bit later, maybe 18,000, but it's well into the Heinrich stadial. And again, the Atlantic is very late to the party. And you cannot explain that difference sedimentologically, sedimentation rate or anything. And so what we're seeing is the Pacific and the Indian Oceans oxygenation, and therefore loss of CO2 and ventilation, reintroduction of CO2, led the Atlantic by some 5,000 to 7,000 years. That's pretty impressive. Why? So I'm going to get back into modern ocean circulation. Generally speaking, we used to think that all of Antarctic bottom water formed in the Weddell Sea. We now know that some of it forms in Prince Bay, some of it forms off of the Delhi land. And if you look closely, you can see the little red circles where this forms. And so this is a wonderful modeling paper showing two things. The major sources of Antarctic bottom water today, major formation zones, and that we know that they have their different flavors. And so you can see the influence of these different bottom waters. So if your bottom water in the Atlantic is coming just from the Weddell Sea, and in the other zones it's coming from other places, then they may have been more different in the past, right? If we take away that that homogenizer that is NADW today, we can imagine that we'd have different flavors and different timing of that. And so those red circles are our cores, just on a couple of maps because of the different things. So our cores are these ones, and they're primarily being influenced by different AABW formation zones than the core that I just showed you from the South Atlantic. So if you don't have an ADW to homogenize them, why would you be surprised that they're not doing the same thing at the same time? And so our working theory is, and this is pretty standard, there was ice covering the and we know that there was a lot, CS extended much further out into the Southern Ocean in the LGM. So this water that's and we didn't have an ADW, so we were having, this is our main source of deep water. If we cover that in the LGM, we don't release CO2, but if we move that back during the Heinrich, then we're ventilating these waters, but we still haven't gotten this water back to look at sources in the Atlantic. So sea ice and how far it extended shifted back early, allowing both shallow and deep ventilation in the Indian and Pacific sectors. So, and the evidence for why did that happen is we see early mid-latitude warming of the Southern Hemisphere. So I want to focus in, this just happens to be work that we did, but there are other people who've shown the same thing. And what you can see here, it's just 37, 40, and 45 south sea surface temperature records with time. And I'm going to put a line here at 37,000. You can, I exaggerate a little bit, but you can see with that line there that it warmed at mid-latitudes first, and then that warmth spread south with time. And that warming was well before that dotted line is our 16.5 halfway through the 100. And that was in the middle of this shutdown of North Atlantic deep water. So you've got a mechanism, and actually, just want to remember to say, the orbital forcing is such that this was the time of maximum insolation in the Southern Hemisphere. Is this about 20,000 years ago? And there's many ways to calculate that. We can talk about, but yeah. So there's warming at mid-latitudes. It's being translated to the Southern Ocean, and there's insolation reasons that we would assume that. And so you can see this is just to draw that southernmost one. You can argue about that blip, but the final, the irreversed warming happens quite a bit later. Okay. So what we do know, so we think that these wind shifts associated with this warming. So yes, wind shifts came associated with that warming. So this is a study by Karen Kofeld, where she assembled terrestrial and marine records, and basically what her conclusion was, it's a little bit equivocal, but if you look at this, the data supports this shift northward of both winds, and the evidence from the sea surface temperature and stuff is the fronts shifted north in the LGM. Yeah, and so we know it was the Southern Ocean was expanded, the winds were retracted, so you have another mechanism for reducing exchange in the Southern Ocean. It's the CS extent, and it's the retraction of the southern westerlies, which go along with the ACC, by the way, during the LGM. And so particularly here, we have some equivocal information, but some of the modeling is shown. So it was kind of equivocal. So that was 2013, right? So this paper came out just a couple of months ago, and what they did was they took Deloitte. Now they've changed the perspective, and I've just used their figure. But what you can see here is we had equatorward shift down of the front. So they did an analysis of a bunch of, and I don't have time to go through their paper, but I have a few extra slides that people want to know, showing that on average in the Indian and Pacific Oceans, the winds and the fronts were 6 degrees closer to the equator, and that progression of those. So now we have a time series of frontal and wind movement, and sure enough, it moved way closer to the pole. So opened up, blew on the Southern Ocean, and it helped the upwelling and the exchange right when we think, right where we see that CO2 going. So underneath this pole, where the westerlies were in red, is the CO2, and they track right on top of each other. So the CO2 came out of the Southern Ocean because the winds shifted and the fronts shifted, And the reason they did that early is because of that warming is my, oh, and I want to give a shout out here. This is lovely. This paper here, they suggested that it was shifts of the winds in 2006. And they're just saying, yep, they got it right. Sometimes it's nice when you're right. Not my team. That's Robbie Tagweller's group down at GFDL in Princeton. And so I just want to talk about this, the differences between the sectors and sort of unpack that last little message. So this upwelling, it's not just the classic view is the one I showed you where the water comes up and it's the same everywhere. No, it's not. Just as we have different zones of AAPW formations, we have different zones where the upwelling is focused, and it's usually where there's a bump or a constriction. So we have lots of, this is just a model by Brady et al. This is a Joel and Russell's postdoc, if any of you know the field. And so they're showing, these are the crossings. I think it's Lagrangian tracers and where they cross 1,000 and 200 meters. So this is AAW and this is smooth water. But you can see focused in Drake Passage, Crozet Plateau, that bump there, Kerguelen Plateau and Campbell Plateau. I would like to note that this is restricted to south of 45 South, and there's some other really important bumps that they didn't get, but that's where our core location is. So I'm just going to show you data from there shortly. But so this recent work by the Devin, Putnam, Russell et al. Talked about the identity shift. So not only did the fronts, so this is today, this is the subtropical front. We now have evidence that not only did the front shift north in the LGM, that's right, but also that there might have been a shift of the East Australia current. All of you Finding Nemo fans, that's the EAC, and we think it did something very different. They think it did something very different in the LGM because it had to get around New Zealand. But basically, so associated with these wind shifts were when we see these wind shifts in time, like I've just shown you with the Gray et al. Data, it really maps right on top of the CO2 release. So I want to show you, finish up. Am I okay on time?
Oh, yeah, yeah.
Okay. Maybe I've gone too fast. Some of the data we have from our recent cruise to the Southern Indian Ocean, we got a bunch of cores, and we're trying to do the same thing here that we did. I just showed you from New Zealand and off of Brazil. And we're not quite there yet, but we do have some really exciting preliminary data. So this is just a shallow core of ours from 1,000 meters. So we're sitting in the bottom, this core, it was taken from where mode water and intermediate water is forming in the Southern Ocean, right on one of those hot spots. And so first of all, I want to show you our temperature record, our sea surface temperature record from this core. And we've got 2 4Ms, so we have 2. Makes you feel better if they both do the same thing. And so, yes, we see this early warming. Heinrich Stadial 1, that's my beginning of the LGM, and we're seeing warming early. And we can take this Dello 18 on those 4Ms, and this is my grad student, Ryan, and it's just been submitted. And what we can do is we can back out a salinity. And so what's really exciting here is that what we're looking at here is that we know the deep ocean was saltier, the deep Southern Ocean was saltier in the past, and this is the mode water, right, and the intermediate water, and it is the same salinity before and after, but we see this pulse of salinity coming up with that first wave of CO2 rich water. And what our hypothesis is that water then gets entrained into Agulhas leakage and into the Atlantic, and might be the salt source that reinitiated the deepening of NADW. So that's a different story from the CO2 story, but I have to tell it to you because it's pretty exciting if we're right. And my postdoc Nat Umling did the C14. Now C14 is also a very, very good record for respired CO2. Not so much respired CO2, but the age of that water and the age of that carbon. And so one of the things we see in other places is when that CO2 is released, we see the old water, right? If it was down there holding on to the CO2, it's older. And so right when we see this salinity, we see this extreme aging of the surface and the deep. So this is our phytoplankton, our planktonic forams and our benthic forams. But this benthic, remember, this benthic forams are 1,000 meters. So we're seeing in this intermediate water that's forming, we're seeing this old water coming up, and this old water, and the age of that water indicates that it's been down there and accumulating CO2. So, you can't just run the biopump if it's coming back out. You also have to slow the circulation down to hold that CO2 in. And this is fundamentally a signal of where that CO2 came out, and it was coming out in the Indian Ocean. And what's really interesting is, we see the planktonics snap, in a sense, go back to normal after the Heinrich, but we're still seeing that slow seepage of the CO2 after that. Let's see, I think that's what I want to say about that core. And if we just put it all together, it's sitting right with that. That's just the Will Gray record. Now going the other way, because we're paleoceanographers, but you can see as those winds shift up, they're shift from far north to south, we're pulling that CO2 out, and we're pulling up salty water that was trapped in the deep ocean. So our geochemical evidence kind of lines up nicely with the timing of the northward wind shift fronts, the release of the CO2, and everything else. And Ryan's done some nice change point analysis and stuff. And this is actually sea ice extent, which lines up with it too. The sea ice was going down, the winds were going up, and the CO2 is coming out. And if you've ever been in the Southern Ocean, you can believe that with the winds, we can get a lot of CO2 out really fast. Yeah. And so I just want to leave you with this picture to pound home. So that CO2 coming out, that's the record we've seen. This is the CO2 record we've been looking at over and over in this talk. This is the C14 of the atmosphere. So part and parcel of that story, and I haven't talked about it, but if the CO2 if there was CO2 being trapped in the ocean, then the C14 of the atmosphere has to have been, and this is a reverse, has to have been higher. So as we exhale that old CO2, the C14, or the reservoir age of the atmosphere, has to decrease. And this is one of the most powerful, this is the second most powerful piece of information, and I've saved it for last, that CO2 had to have come out of the ocean, because the C14 of the atmosphere mirrors, and I've drawn it in reverse order so that it follows that CO2 release. And this is just to show that this is the sea ice. So more sea ice is down. So we're seeing, as we're seeing this stuff out, we're seeing the sea ice reduce. And this is just the Antarctic temperature record. So those are all the other proxies that go along with it. I'm just trying to, I'm just like, and if you didn't believe that, you can believe this. So to take home messages, the Southern Ocean warming and ice loss led the ventilation and led the fronts and the wind shifts, tracked the CO2 increases, and they all led any increase in AMOC. So it was not the Northern Hemisphere ice sheets driving the release of CO2, in my opinion. You can argue with me, that's fine, a lot of people have, but basically our working theory right now is physical processes in the Southern Ocean were central to the initiation of the deglaciation, and at least the first half. And I think that's my sunset photo. Thanks for your attention. What did I talk about too fast? Right. Yeah.
Oh yeah, very interesting. Lots of information.
I know, lots of data streams. I apologize. I tried to explain each one.
So this is more a perspective, or maybe something that you could comment on, which is sort of maybe a different perspective on why the deep ocean stagnated and why North Atlantic deep water couldn't get into the Southern Ocean or less that it couldn't get into the Southern Ocean.
Or significantly reduced. I mean, we can discuss quantities, but we don't have any information on that. But go ahead.
This is based on like papers by Raf Ferrari and
oh yeah.
Maybe you're familiar with, but
yes.
But if you add eddies, the sill depth matters a lot less. The precise depth of the sill matters a lot less for the Garnier transport across the ACC. Right. But if you do raise the interface between the deep water, now the intermediate water and Antarctic bottom water, the argument goes that you raise it above the depth of the mid-Atlantic ridges, or not even Atlantic, the mid-ocean ridges. And so you decrease the mixing between those two water masses a lot. And so there's no way for the Antarctic bottom water to basically get out of the bottom of the ocean. And so it just stagnates there until, you know, it either builds up heat and convects, or you have something that shifts the upwelling sites due to shift in the wind and finally draws it out. And I don't think it changes the story that much, but it's a different reason.
No,
why
it doesn't
it's
change the story. In fact, that work came out in 2014, and it very much informed my thinking. And the only, so that essentially that is absolutely has to be what's going on in the North Atlantic, because you've got the 2-layer ocean. But you still got a 2-layer circulation in that one, and in the Pacific, you really need to think about it as a 3-layer. And so the two are not mutually exclusive. I think that one's more, if I can put it this way, more correct in the Atlantic, and you have to have something else going on in the Pacific to explain that. But yes, that slowing down and that so what we call in the field is the shallowing of the geochemical divide absolutely helped cap. That's fundamentally, and that's one of the things, if you look at that, the data I showed you, you know, the time series, that was actually one of the exciting things, that when we saw that intermediate water wasn't being ventilated. So we had that raising of the geochemical divide. And so that's definitely it. But what it still presumes is that there's the Ferrari one presumes a continuum between the formation of water in the North Atlantic with the other two basins, which may be tenuous according to what we're saying. So yeah, they're not mutually exclusive, but I would say I think we kind of tweaked it. But yeah, no, that was a great paper. In fact, in the 2016 paper, which we published, we said, look, it's 500 meters shallower, and that's exactly what Ferrari's paper listed it as. So yeah, good question. Anybody else?
I was really interested in the changes to wind patterns that you talked about. I studied albatrosses and things in the Southern Ocean. But I was getting a little confused because my understanding was that there have been forward shifts in the westerlies in recent decades.
Correct.
And then, but I was confused when you mentioned the northward shift.
Okay, sometimes I misspeak, so let me make sure I didn't say it wrong. I just every once in a while, you know, my mouth gets ahead of my brain. But we had equatorward shifts of winds and fronts in the LGM. And as we warmed the world, and this is what's happening today, things shifted back poleward to where they are today, where we're ventilating the ocean. And when we shifted them north, the ocean didn't breathe out as much for both. The winds were in the wrong place, and we had sea ice. And then as we shift them south, which is what we're seeing today, we then enhance that exchange, and when we remove the sea ice, we can have the bottom water, the Antarctic bottom water, form more not kind of efficiently, more forming, anyway, that one, more ABW formation as well. So if I spoke, I may have misspoke, but that's the general idea. Okay, yeah, thank you. In case I said it wrong, now everyone knows what I meant.
I'm also curious about the winds. Do you, can you kind of briefly say what the evidence that's used to indicate what the winds are doing?
Yeah, no, I'm doing that because I spent the first half of my career in the Southern Ocean doing sea surface temperature and saying that the gradient of sea surface temperature tells us where the winds is. And if you talk to it, what I then was informed was, yeah, sea surface temperature has nothing to do with winds, because the important winds are like, you know, the next layer up in the atmosphere. So I realized that talking about winds is somewhat I was informed that I cannot tell anyone about winds in the Southern Ocean based on temperatures and measurements from the surface ocean. And I will accept that criticism. However, the one that I showed you from what we're looking at are gradients. And so we're assuming that if the gradients in temperature and W18 that we see today that are associated with fronts, they are associated with fronts. So we can say we see the fronts move. So then one must the thing that
SST or fronts in the atmosphere? Which portion of
Fronts in ocean fronts.
Okay.
Ocean fronts. And so the work that I showed you from Will Gray's group, they are making a connection between those gradients, which are associated with ocean fronts, with where the winds are placed. Because today those fronts are located where the winds are. They're tied to the winds. And so that's the 3-step thing. And I realize that may be tenuous, and I'm not enough of a meteorologist to say anything more than that's my
Just
understanding.
as a quick follow-up, do you think that that's the same evidence that the Togweiler papers, is it the same kind of methodology that he's using to? Because I think he's done a lot of work on the wind shifting, right?
Yeah, he uses, I think he uses box models, which was some of the arguments against that association, but he was able to show. I'm trying to remember. I haven't read that paper long, but yes, that's Robbie's work. Robbie did those initial analyses, and they were because basically the upwelling is where they're associated with the winds.
Yeah.
I think it's the word, it's been a long time, it's like the curl of the wind stress can be associated with the fronts.
Yeah.
And that's important. Yeah.
Really, so you're talking about the shift in the wind, but is there a relation of the change in magnitude of the wind as well, or you just see that for a little bit?
Well, I'll go back to my caveat and excuse that I just said. It's like, well, we're looking at fronts, we're looking at gradients in change in water properties, which are associated with fronts today. I don't know if anyone could tell you about wind speeds. I think some of the terrestrial stuff might, but yeah, it's 2 layers of assumptions that I'm not involved. These are not my work, but yeah, I rely on them. But yeah, I don't know. I think one would assume from first principles that as you move winds north, right, you're taking that whole southern westerly wind belt and you're making it bigger. And so the assumption, the first order assumption is as you move north or equatorward, your winds are going to decrease because you've got, you're spreading the same amount of energy out over a bigger space. And so as you move it south, it would intensify. But I don't know if anyone could tell you definitively what the magnitude was. We can tell you the magnitude of the upwelling and the nutrients, and then we have to make assumptions. How's that? Is that good? Yeah.
All right,
Sorry, I pick forums and burn them for a living.
before Bob gets to ask the last question, are there any students who want to ask a question? Student question. All right, then Bob gets to ask us.
The last question.
I'm still a student, sorry,
In
of all of this kind of thing. And I'm wondering, you talked about manganese as an indicator of oxygenation, but at the same time, you were showing that productivity is changing the the focus of productivity and the quantity of productivity is altering. And both the carbon flux and the oxygen content of the water will influence the manganese mobility and focus within the sediments. And I'm wondering how that's separated out, whether you're just talking about productivity controls on manganese or oxygen controls on manganese. Or
Well, if we, let me see, can I? Oh, no, I'm still, okay. If I just go back, maybe I can go, oops, that's my ACC, okay, I'm gonna go backwards. Back. Let's look at that one record where they had, so I'm gonna say, we don't see the productivity in our cores going up in line. Those are our cores in the middle with the others. I can't speak to anyone else, but if you, this is the Jakarta paper, and they also looked at uranium. In that core, and those, so they see this, they have a oxygenation core from the pathogenic uranium as well changing. And so you can use a couple of things, but yes, you're right. You're very right that the that if we increase our organic carbon in the sediments, then we're gonna have lower oxygen in the sediments, which is where the signal is coming from, and it may be a sedimentary artifact rather than a deep water artifact. And I'm trying to remember, I don't know what the organic carbon are in the ones that I showed you next. Whoops. Here. In these, but I can tell you that we're actually seeing across the, if I remember right, in at least the one core we've worked up, we're seeing a reduction in organic carbon across this boundary rather than an increase. So we see it both. So we're not seeing that same. Oh, these cores are too far north for the opal, but we did some TOCs, and I'm just rolling around in my brain. We had I think that the preliminary TOC data that we have wouldn't support that being a productivity signal, translate a sedimentological signal, but good point. That's why I said we did run, Aiden ran, there's a geocarb model that you can run, and you can input the total organic carbon and a couple of other things. And that was that analysis that brought him to the idea that you cannot explain the difference between these different sectors on sedimentology, but that's why it's in prep. I can answer that question. Let me call Aiden and I'll let you know.
We can talk about it later.
No,
Thank
but it's
you.
a good question, because this is for those of you who I totally scared with all these different proxies. You have to know your proxies, and you have to know the other impacts on them. So when I say winds, what I mean is ocean fronts. That's the only thing I can say with definitiveness, but people will make that extrapolation. And I do when I speak. I usually don't write that in my papers because I have to be more careful. Well, no, you go through review and someone goes, yes, Bob's question. And I'm like, okay, all right, we'll change that. We'll be a bit more conservative. I still think this story hangs together, even if I'm conservative about those interpretations.
Okay, then let's thank the speaker.
Thanks for your attention.